We are here to present Rubicon today, one of the libraries that we have open sourced last year. And we're also presenting how Capital One is into open sourcing and more about open sourcing, like how we embody the principle of open sourcing tomorrow. So please try to join us tomorrow for another talk. So why are we here? Why is Capital One? What's Capital One going to do with open source? How are we into open sourcing? To start off, giving a brief overview, Capital One is one of the fintech company. We are basically invested a lot into technology. We house around 11,000 associates, 85% of which are engineers. And we are very proud to say that we are one of the tech companies who are on the cloud for the, completely on the cloud. We do not have many colos or any on-prem locations, so we are completely on cloud. We have automated DevOps and CI/CD approaches. Most of our work that we do is automated, so we don't do a lot of release management in the sense that doing one major releases at a time. So we are heavily invested in technology. How are we associated with open source software? So Capital One has made this announcement wherein we said in 2014, we are open source first. So anything, if at all, there is a library that's out there or a tool out there that's been open sourced, we try to leverage it. And our first contribution to the open source community has been in the year 2014. We also sponsor Finos, Python, Continuous Delivery, and the Cloud Native Computing Foundations. Apart from it, we have almost close to 40 open source software projects. We will talk a bit more about them tomorrow, but to name a few, Data Profiler, Rubicon-ML, Hygia are some of those things. We have invested for years to build the culture and governance required to be open source first in a highly regulated industry. So you are all aware for a fintech company, how regulated it is, how much explaining you'll have to do about what you do and how you do it. Why are we here today? So we are here today to present a library called Rubicon-ML. What does Rubicon do? Rubicon is basically an experiment tracking library in the phase of model development life cycle. For most of you, if you are aware of how a model is developed and what exactly is the process, you understand that it's a very, very iterative process. You start off with exploring the data to find an initial set of features for model training. Then you go explore these features as to what is the right feature to use, why do we use it, and how exactly does the scoring or the coefficient changes with these features. And you try different modeling techniques, like what sort of an algorithm are you using, why are you using it, and what happens if I change the modeling technique. And it's such an iterative process that after doing all this, and trust me that it's not just moving along the stages. It takes months and months to figure out all these parameters, coefficients, and the modeling techniques. But after some time, you realize that this probably is not the right parameters that you should be using or the modeling technique that you should be using. So what do? We go back to our state of what is our data? How do I explore it? And what are the features that, again, I'll have to choose and a different modeling technique. So you understand that this whole process of actually developing a model can take up to a year or two, depending upon the size of the model, depending upon your size of the data, and what sort of an output are you looking at. And every single time that you actually create a model, fit the model, and run it, the tracking part is the most tedious, right? Especially considering that we are a fintech company, we have to go explain to our model risk office as to why did we choose it, right? Are we doing the right thing? There is no bias involved. There is no bias involved in any of the features that we are defining and stuff like that. So to say the least, the tracking of the experiments is the most complicated and tedious process. So we said, why don't we develop a library that basically helps the users to track these experiments, right? especially when you're a model developer or a data scientist, the logging of the experiments or the tracking is not your primary focus. Like, you are always in a rush to fit the model, get it to production so that it starts performing. And if at all you go and tell a model developer, oh, you have to track every phase of your model development life cycle because you have to go and explain to your regulators, to your model risk office as to what you're doing, probably they're not going to say, like, oh, this is something that I'm going to focus on, right? So we said, fine, we will take that particular complexity out of the equation. We will develop a library which will basically ensure that every experiment that you're trying to run is reproducible. It's auditable, right? Because at any point of time, if my model risk office comes and tells me, hey, what parameters have you used? What has been the output at this particular point? And what was the status of your code at that particular point? Are you doing any hacks? Are you doing any temporary fixes to adjust the coefficients and stuff like that? We should be able to explain our answer, right? And at the same time, to some extent, it mitigates risk. Like, oh, I remember I did this, or I remember that this was the right way, or this is what I thought was the output, is not something which will fly with our model risk office or with our regulators. So it automatically regulates the risk if you actually track these experiments in a very nice manner. And again, as I said, it has to make sure that there is fairness, there is no bias in any of the decisions that you're making, So we said we will develop a library which will basically help the users do all these things. And that's basically what we are talking about as Rubicon-ML. So what does it do? As if you've seen in any standardized tooling, there are so many ad hoc solutions that you develop, If you talk to any developer, most of the developers have the tendency to implement their own logging, right? Why do I have to learn a new logging library, or why do I have to understand something, or why do I have to try to see whether it works with me or not? So what happens is all these basically thoughts give rise to a lot of ad hoc solutions. We want to take that out of it. And again, as we just said, logging is not your primary outlook when you're developing a model, right? But again, it's very important. We all understand that, but definitely it's not something that I will prioritize over developing a model. And tracking experiments, it's understanding what was the status of your Git, how many experiments did you do, how did the coefficient change, how did the output score change, is something that you have to do it. And of all these things, again, the infrastructure is another thing that we all struggle with, right? How do I run it? Where do I run it? Where am I going to keep these logs? How am I going to share these logs with other people, right? So those are the constant questions that you ask yourself. And that's where Rubicon basically comes into picture and shines. So what is Rubicon? Rubicon is a lightweight open source Python library. What does it do? It offers standard logging process for ML experiments. It integrates with most of the open source tools that are out there, some things that you have seen, Prefect, Git, and all these standard libraries. So what was our philosophy in developing Rubicon? Rubicon basically leverages all the open source libraries out there. We did not develop anything from scratch. The philosophy of the team and of Capital One has been the same across years. If there is a library out there that you can leverage, use it. That's the first thing. If it can be, try to see if at all you can contribute back to the open source to make it work for you. But again, if at all it is very customized, if it has to work only specific for Capital One scenarios, then try to do all your development inside, inside your repos and stuff like that. So we have used something called as fspec, intake, and plotly. These are the three basic libraries that we rely on. What do? So we told just now that when we are talking about Rubicon, we did not want to define what sort of an infrastructure you have to use. Neither do we want to put a label on where should your data reside, because whenever you see some of these libraries out there, you say, oh, your data has to reside on an S3 bucket if at all you're using AWS. It has to reside on XYZ database or somewhere. So we said, okay, we will take the complexity out, use FSpec library. You decide where you want to live the data, like, whether you want to run experiments locally, you're generating on your own laptop, run your experiments, or it can reside in a database, or it can reside on an S3 if at all you're using AWS. So the user has the complete freedom to decide where his data lives. And that's how Rubicon supports various backend options. And once we start getting into the code a bit, you will see that it just takes a simple statement from you saying that, hey, this is where my data resides, and this is how I want to use it. The second thing that we are talking about is another library called as intake. What does intake do? When you're talking about running your model multiple times, when you're conducting experiments repeatedly, at some point of time, you come to a particular set saying that these are the parameters I'm going to use. This is my experiment, and it's yielding the results that I am looking at, right? So what happens? You have to share it, whether it's with your team members you want to collaborate, or whether it's with the model risk office, or with your regulators, for all I care, right? So when you're talking about sharing these experiments, how do you share these experiments? It's not feasible that you copy, download, or generate PDFs or PowerPoint presentations and send them along. We put it in one particular location and use this intake driver to either collaborate or to share the experiments of the results of our experiments. Last but not the least, okay, you have done your experiments, you have shared it, but what use is it if at all I can't visualize these experiments, right? I want to see how is the data trending, like, if I use these parameters, what sort of trends am I seeing in my output? That's where your Dash and Plotly come into the equation. So the Rubicon library has some widgets that we have developed. Again, these widgets are something that you control, like, what do I want to see? What do I want to add to what I want to share, right? Those are some things that the user controls, and these dashboards and widgets have been developed using Dash and Plotly. So at the top of the Rubicon, you have something called as a project. We'll go, Ryan will start talking a bit more about the actual code, but at the top of the Rubicon, you have something called as an experiment, right? Project. All you have to do, if at all you have to put it as a part of your model development lifecycle, is you have to create a project and create an experiment and start tracking. It will automatically track your parameters. It will automatically track your output metrics. And it is all logged in one particular location. And the beauty is it's basically structured in a hierarchical fashion. So you open any experiment, it will show you, hey, these are the parameters that you've used. This was the output at that particular point, right? And apart from it, it's also integrated with Git, which means to say, for this experiment, I actually associate with a Git hash to see, like, this was the status of my code when I'm generating this particular experiment, right? All those things are automatically tracked for you. All you have to do is set some simple flags at the beginning of it. So with that, I will actually give this to Ryan to walk us through the code, what we have done.
All right, thank you, Sri. Let me go back real quick to this one. So just to quickly piggyback on what Sri said there. So essentially, Rubicon is very lightweight in the code within the library itself. We rely very heavily on existing tools to make our lives easier. Essentially, the Rubicon code base is defining a domain language for your model tracking, as Sri mentioned, with the projects at the top level, and your experiments being your reproducible runs. Other things they include basic key value pairs like parameters and metrics. You can track your features as well. And then we also have more binary objects like just general artifacts, which can be any binary file that you dump, or data frames, whether that be Dask or pandas, or other things are a little less natively integrated, but they can work as well with a little finagling. So to hop into the code a little bit, throughout this whole throughout this whole thing, I'm going to be kind of leaning into the scikit-learn style of developing pipelines because this is how we generally tend to encourage our other developers at Capital One to write modeling code. And this makes it easier for us to integrate Rubicon, as I'll show in a minute. But first, this is just what a very simple integration would look like if you were doing just manual logging. So in the code cell on the bottom, you can see that we are instantiating our Rubicon object and simply telling it that we want to log to a local Rubicon root. And then just creating a project and an experiment and logging some features and parameters and metrics. So, this is obviously very manual. If you have an existing pipeline, it should be very clear to see, yeah, you can just pepper these statements all over the place to get the logging that you want. But, if you have a giant code base, that can be a little bit cumbersome. So we do offer a lot of other ways to do this a little bit more cleanly without as much like manual work up front. Not to say that we can completely eliminate that, but at least make it a little easier. So what we have here is our drop-in replacement for the scikit-learn pipeline, which is simply our Rubicon pipeline. And it is purely a superset of the existing scikit-learn pipeline functionality. We didn't override anything that already existed. We simply re-implemented the fit and score to call the existing ones of the superclass and then log to Rubicon. And what we're logging to Rubicon is essentially every single input to the fit, or to the instantiation before the fit, I should say, and any scores that are produced by the call to score. So if you take a look at the code on the bottom here, this is where we're just retrieving our experiment from the pipeline and printing out the things that were automatically logged. So if you take a look at the parameters, you'll see that they are formatted in the way that scikit-learn would expect them. So if you were to dump the parameters of your Rubicon experiment straight back into your pipeline as like keyword arguments, it should automatically be able to reinstantiate that same pipeline so that you can reproduce it for whether that be auditing purposes or just wanting to rerun your pipeline in general. So this scikit-learn integration is what we generally tend to encourage users to use when they have like more custom code bases. Essentially, we'll ask them to format them into estimators to fit scikit-learn's estimator spec if they haven't already, and encourage them to use this pipeline for the most comprehensive but also simple upfront or little upfront cost logging that we offer. So a quick aside on some other logging backends. The one that I just showed was just local logs. So Rubicon, whenever you're instantiating it, is just creating an fs-spec file system under the sheets. If you're not familiar with fs-spec, it provides file system or bash-like file system operations like things like cat, remove, or rm, those kind of things, and it just enables you to easily hook into any backend storage and do these more easily. And libraries like pandas and Dask are built on top of fs-spec to handle their file reading and writing. So we're pretty confident that it's a good solution that will be very highly, maintained, well maintained. That being said, when you instantiate your Rubicon object, you're essentially just sending through a persistence and a root directory, or in the case of this first one where we're just logging in memory, we don't even need a root directory. So, this would be for things like just like setting up your project and experiment, trying to figure out what exactly you want to log. You can log things to memory, so you don't need to clean up after yourself. Once you're ready to start doing some actual local testing, you can log it to your local things, or in some instances, we're running on remote servers where we're running to just logging to mounted file systems. That is also encompassed by just the regular file system logging. And this bottom one here shows S3 logging. So we primarily use AWS for a lot of our cloud stuff, so we support S3 as like a first-class integration here. Now, like I said, under the hood, when you instantiate like this, we're basically just setting a file system attribute on the Rubicon object that is the fs-spec file system. So if you are interested in any of the other backends that fs-spec offers, you can just override that, and things should work nicely. Now, I say that because we have fully tested the memory, the local logging, and the S3 stuff because that's what we regularly use. So I don't want to make any promises that other stuff would work perfectly. But if you are interested in logging Rubicon to other places, it should be a very quick, quick PR to the library to support it as a first-class backend option. And this is essentially the whole point of this, as Sri mentioned, is a lot of the existing solutions we've found tend to require a dedicated database solution of some sort. And a lot of our model development teams don't necessarily have dedicated engineering folks that, can spend the time to make sure that infrastructure is up and running. And we also don't have, so Rubicon actually used to be a like centralized service where there was still a Python API or a Python library that would log to an API and would actually store things in a server, in a centralized server within Capital One. Ultimately, we decided to move away from that because even in that world, there were then the instances of, like, if that server goes down, people's models can start running into trouble, and we don't want to have to deal with that. We don't want to be causing models to fail or anything. So when we use the data stores that people are already using, like, if they can't access S3, there's probably a bigger problem than us. So that kind of keeps our hands clean in terms of too much overhead maintenance. So onto the sharing part of this. As Sri mentioned, we leverage Intake, again, another open source library, I believe developed by some of the same folks as FSpec. So what Intake essentially does is it enables you to share data with like the least amount of information possible. So what we're doing in this top cell is publishing a Rubicon experiment, and what publish does is just create a YAML file that Intake it knows how to read, and these YAML files define the bare minimum that are required to recreate an experiment or to pull it from wherever it's logged. So if you take a look at the output here, this sources YAML, we can see that we have our experiment ID, our project name, and the URL path to that project. So that's all the information you need, assuming you also have access to this particular location. So if this was an S3 bucket, it would be expected that the user this catalog was shared with would also have access to that S3 bucket so they could retrieve those experiments. And of course, that also adds in like the layer of security. What we're passing around here, this YAML file, if people can't access the data, then we're not sharing anything important. So this file is pretty safe to be passed around without worrying about, any important metadata just being out there. And then Intake itself in the bottom here is capable of loading in these catalogs, pretty straightforward. Using the Intake library itself, you can just recreate these Rubicon objects. The shared experiments list that is created at the bottom there are back to Rubicon objects, and they can now be used as any other Rubicon object would be. One other quick aside on this, so in the publish function call, we're giving all of the experiments for this one particular project. That's not the only way you can do this. So you can publish multiple experiments from multiple projects, and this can be useful when, say, you have a handful of things in different S3 buckets that you want to compare, maybe from some different users, or if you've got some local logs that, or like not necessarily local because that's kind of hard to compare, but like on a mounted file system somewhere. So it enables you to mix and match in terms of like actually sharing these projects out. Whereas when you're writing them, you're more so like picking one thing that you want to do. But this enables people that are logging to different backends from different places to ultimately collect and share things together. So after you share the experiments, logging, you can go through your notebook looking through the attributes of these Rubicon experiments. They have lots of details on them. And a lot of people do like to use that. Under the hood, Rubicon's just writing JSON files, so some people will just purely ingest that without even using the visualizations or anything, and put that into whatever store or lookup they want to for those kind of things. But we also offer our own visualizations, and a lot of these are more like experimental kind of visualizations for when you are playing around with your models. So these are all designed as widgets that can be rendered inline in Jupyter notebooks, as well as hosted on, just hosted on a server and whatnot. And that's all powered by Dash and Plotly. So we're not dealing with any of that code for actually showing these widgets or running the websites or any local sites that are spun up from this. Dash has plenty of great documentation for hosting Dash apps in like Docker containers. So if you want to start sharing these dashboards, there's plenty of documentation out there that's purely just Dash stuff that'll show you exactly how you need to do that. For some of our particular visualizations, I'm not going to go through all of them. Essentially, We have a framework built into the library and some instructions for how people can contribute their own visualizations. We often find that developers, they tend to like the ones we have, but every now and again they're like, we also have this one that we're going to use with it. So we always encourage them to pull that back into Rubicon so we can kind of collect them all. This one here is just a very simple experiment table. It's just listing out all the experiments you've got logged and their inputs and outputs. We've got some links out to GitHub if the code was, or if the experiments were logged with the GitHub logging enabled. This particular one shows some data frames. So as I mentioned, you can log data frames to Rubicon. This is just a way to visualize them all on one particular chart very simply. So what we're doing here is just like this visualization under the hood is taking in 6 experiments and just rendering the 6 data frames logged to those on one axis here. And another aside, as I showed with the intake stuff, when you're inputting into these, when you're inputting experiments to these visualizations, you're inputting at the experiment level, so they can be some experiments from location A, some from location B. So you can use this to compare with colleagues that are logged into different places. And then we also offer the ability to combine these visualizations into a dashboard. So essentially, if you're making a Rubicon dashboard, your controller is going to be the experiment table, and you can select and deselect the experiments in that table to control the data shown on the other widgets within the dashboard. So if you wanted to, like this right here is just showing 2 things. We have the experiment table up top as well as a metric correlation plot at the bottom, and that's just showing some parameters on the first 3 axes as well as the accuracy score on the final one. All of these are interactive, and that's all through Plotly and Dash. They've got some really great built-in tools. Like this, the code that's rendering this plot is very, very, very simple. Like all of the hard stuff is in Dash. So again, we're making good use of the existing stuff out there to make the good stuff for our users, but very quickly, very simply. And as I mentioned, it should be fairly, like anyone familiar with Dash and Plotly should be able to quickly make a new Rubicon visualization to add to the suite. So that is the 3 main pieces of Rubicon at a very high level. So before we wrap up, I want to talk a bit about how we actually integrate Rubicon into workflows at Capital One. Unfortunately, this is a little less codey because we can't share as much of that stuff, but I'll try to get the point across as best I can. So essentially, we designed Rubicon to be a jack of all trades because, as Sri mentioned, we have a lot of teams that had already had very ad hoc solutions. So we wanted it to be fairly lightweight for them to switch to Rubicon so that they didn't have to rethink their entire logging framework. But at the same time, that also means Rubicon's a master of none, and at least not without a little help. And that basically looks like a bit of an upfront cost to really dial in the type of logging that you're looking for. So that's to say, one time at the beginning, you're going to need to figure out, I want to log X, Y, and Z inputs. I want to log X, Y, and Z outputs. I need these data frames. I need these artifacts. But once you've got all that figured out and coded into your pipeline, whether that be with the automatic logging or some of the more manual stuff, if you've got a different format, then every single time that pipeline is run, you'll be able to make a new experiment with those things. Everyone who's rerunning that code will have the same input-output data to be able to compare to one another whenever they need to. Right, and then so the way we kind of tie that in at Capital One is, as I mentioned, we encourage users to follow the Scikit-learn paradigms. And at an even higher level, we also develop some. We have an internal library. We're also big fans of inner sourcing at Capital One, so we try to make all of our code available on our internal GitHub that can't be published. Like to the public one, like Rubicon. And we essentially have another library that is Scikit-learn estimators that do general ML stuff. From like linear models all the way up to aggregate estimators like grid searches and feature elimination. So we have a handful of those that just have some little Capital One secret sauce in them. And the way we integrate Rubicon with those is that since we have full control of those libraries, we were able to build the logging straight into them. So we would basically encourage users as they're designing their ML code to fit this estimator spec to make sure that in any post-fitting or post-scoring callbacks or functions that happen, they are defining the Rubicon logs they want. and logging them for the users. So now, as a user, if I'm just importing from this other library, say a GLM, if I just call glm.fit and pass it my Rubicon project, I get back a nicely, or that project will now have an experiment log to it with all of the metadata that the team that develops that estimator deems necessary. And that's helpful because, like, a lot of times when we're following this inner source stuff, we may be pulling from repos and not logging enough, not logging the right things. And a lot of times we also just get questions that are like, what should we be tracking? What are the most important things to be tracking? So we can then, we try to define that ourselves by baking this straight into the estimators. And this is kind of different from the Scikit-learn stuff I showed earlier. That's essentially for if you have regular Scikit-learn estimators that don't have this stuff built in. So we wouldn't necessarily put one of these into that pipeline. We kind of would use a regular pipeline at that point, and then let these do all the heavy lifting. And where that really shines is when we start switching up what those pipelines are. So for local development, that might just be, it will just be a scikit-learn pipeline, and you're going to be logging local files to your local file system or to a mounted file system. But we also then, like when we're productionizing our models, we generally tend to use cloud-based solutions. We've been using Kubeflow a lot recently, and Kubeflow, of course, has its own logging, but that's more on like the metadata side of the Kubeflow stuff. It has its own integrations with ML logging, but we've found that using these estimators with Rubicon built into them inside of our Kubeflow components can make life a lot easier for our developers in that now if I run my scikit-learn pipeline locally, if I run my Kubeflow pipeline in the cloud, I will get an experiment from one and an experiment from the other that'll have the same inputs and outputs log to it, so I can easily compare them. So if I'm doing some local development, I need to compare it to like a champion model to make sure I'm not totally deviating from what they're doing. That's the kind of stuff that we can facilitate with that. So yeah, that's basically the big picture of how we try to use Rubicon. We encourage our users to be thinking about it from the start when they're developing these things, so that they can be the ones that are defining the inputs and outputs, and then others can adequately leverage those to do whatever they need for whether that be just making sure your model's performing properly, whether it's for audit-ability purposes, and any fun stuff like that.